Okay, so the prisoner's dilemma, just like our other matrix games, shows us sort of when individuals can benefit from being in cooperative mutualistic association. But obviously mutualism can have effects at the population level too, right? And so people have made population models for mutualism. Whoops. And to think about what those would look like, right, we could start with our single population model that we've used. Again, you don't need to know this equation, but you should know how to use it, right? So this is just the logistic growth equation. It's got our intrinsic rate of increase. It's got our carrying capacity, and we see that it grows with this S-shaped sort of logistic curve, right? So we can consider a plant population that's growing according to the logistic growth equation. I've just changed n for p, but it's got its own intrinsic rate of increase. It's got its own carrying capacity, and it does its logistic growth thing. And then what happens if we add a mutualistic partner that also grows logistically? So it's got its own Rm, different intrinsic rate of increase, and a different carrying capacity, and it does its own logistic thing. How do we connect the positive effects of these guys to one another? It's probably going to look an awful lot like competition. It's just that we're going to switch it to a plus sign, like I said, right? So we can imagine that we take this sort of density dependent term here, and we switch it to a plus instead of a minus, and we put an A and a B like we did before. We make them Greek so that we feel like we're fancy mathematicians. And there we go. So we have a basic model that's rather like our competition equations. You can also do this and make it similar to the predation equations. That works too. It's a slightly different model. Right, so let's start with two individuals like we did before. Let's set alpha and beta equal to 0.5. Remember when we did competition, we put A and B equal to 0.5. We'll set K, both K's to 100 like we did before. We'll set both R's equal to 0.25. My little face might be covering this up, but you can trust me that that's what I did. And so remember when we did this for competition, what did it do to the carrying capacity? Well, it reduced it, right? So what do you think it's going to do when we switch the minus signs to plus signs? I'm not going to bother with the survey because hopefully it should be obvious to you that it increases it, right? So we went now from a carrying capacity of 100, which is what we defined, but we end up with actually 200 of each individual's. That's because of this sort of synergistic effect that goes on between the two populations. As one of them is doing better, you get this positive density-dependent effect that actually allows the other one to increase even more beyond its carrying capacity. It's pretty cool. But there's a weird problem. If alpha and beta are greater than 1, so if it's a really positive interaction, then the populations go to infinity almost immediately. So you can see after 100 generations, I've gone to 1.2 times 10 to the 11. So that's probably not something that actually happens in nature. And it's kind of interesting. Because of this, there aren't that many good models of mutualism, right? So what I've showed you before are basically versions of this, and here they are down below. So we've got the mutualism model I just showed you. I think here we've got the competition model I showed you last week, and then we've got that cycling predation model that I showed you earlier this week, right? And so all of these are forms of equations known to ecologists as Lotka-Volterra equations. And it's kind of cool, actually. Back around in the 1920s, Alfred Lotka was a chemist, and he used these types of differential calculus to explain chemical reactions, and for some reason he realized that he could use them to explain the way organisms interact. And Vito Volterra was a physicist that also used differential calculus to explain physics, and for some reason he also realized this. So basically at the exact same time on opposite sides of the world, Lotka and Volterra noticed the exact same thing and derived the exact same set of equations, sort of two independent discoveries. I think Lotka was an American and Volterra was an Italian. So these are known as the Lotka-Volterra equations. One thing I want to point out, and I'm not going to show you more complicated models, is that these are first-order approximations of mutualism, competition, predation, right? There's obviously more complicated versions of all of those. So, I remember when I was telling you about competition, I showed you this simple one, and then I showed you a slightly more complicated one that had a third equation for the resources, right? So this is the simplest way you could describe competition, but we can obviously make it more complicated, and we should use data to figure out, right? I would argue that mutualisms are one area where there's actually still a lot to learn at the ecological level, right? So we have this hypothesis that we can frame as the Lotka-Volterra mutualism equations. We have this prediction that it's really easy to go to infinity. And we don't really need to do an experiment to know that this is wrong. And so one way to fix this would be to add a third equation for resources again. And now resources would bound the population, right? Because at some point they would get down to their zingy, to their zero net growth isocline, and then the two populations wouldn't be able to go to infinity. But this is still a problem that requires attention, in my opinion, in ecology. So that's the population level effect. And then I think what we're going to do, I'm going to stop this video here and we'll start another one on the other side.